Welcome to Chapter 1, Limits and Their Properties. Section 1.3, Evaluating Limits Analytically. Our objectives in this section are to evaluate a limit using properties of limits, develop and use a strategy for finding limits, evaluate a limit using the dividing out technique, evaluate a limit using the rationalizing technique, and to evaluate a limit using the squeeze theorem. We'll look first at properties of limits. The first property that we're going to look at is direct substitution. This property says that if the limit as x approaches c of f of x equals f of c, then directly substitute c into f of x to obtain the limit. Such well-behaved functions are continuous at c. Many functions fall into this category. On this slide, we're just going to look at 3 of those. The first one says that the limit as x approaches c of b is equal to b. In other words, the limit as x approaches c of a constant is the constant. And you can see that pictured in the graph below. Notice that the graph of f of x equals b is continuous. Therefore, we should be able to find the limit as x approaches c of b by direct substitution. Notice if we pick any c value, that f of c is equal to b. Therefore, the limit as x approaches c of b is equal to b. The next limit is the limit as x approaches c of x is equal to c. In other words, the limit as x approaches c of the identity function is equal to c. Notice when you look at the graph of f of x equals x, that it is continuous. Therefore, we should be able to find the limit by direct substitution. For example, let's say that we choose c equals 2. Well, f of 2 is equal to 2. Therefore, the limit as x approaches 2 is equal to. The last limit that we want to look at on this page is the limit as x approaches c of x to the n is equal to c to the n. And what we want to keep in mind here is that n is a positive integer. Therefore, x to the n is a function like x squared or x cubed that we know is continuous, and therefore we should be able to use direct substitution to find the limit. Now let's get some practice using Theorem 1.1. In example 1, we're asked to evaluate 3 basic limits. For part A, we're asked to find the limit as x approaches 2 of 3. Now we just learned that the limit of a constant is equal to the constant, so we know that the answer here is going to be 3. And we can further validate our solution by looking at the graph of f of x equals 3. Now notice that the graph is continuous, and we just learned for continuous functions that we should be able to find the limit by direct substitution. And if you notice, f of 2 is equal to 3, so the limit is 3. Now let's look at part B. Here we're asked to find the limit as x approaches negative 4 of x. Now this is the identity function, and we just learned that for the identity function, the limit as x approaches c is equal to c. In this case, that's negative 4. And we can further validate our limit by looking at the graph. Notice that the graph is continuous, so we should be able to find the limit by direct substitution. F of negative 4 is equal to negative 4, so the limit as x approaches negative 4 of x is equal to negative 4. Now let's look at part C. Here we're asked to find the limit as x approaches 2 of x squared. Now we know that x squared is just a simple monomial that is continuous, so we should be able to find the limit by direct substitution. So we have 2 squared, which equals 4. We can verify this limit by looking at the graph. Since the graph is a nice, smooth, continuous curve, we can just find that by direct substitution. And f of 2 is equal to 4. So the limit as x approaches 2 of x squared is equal to 4. Now let's look at some properties of limits. Theorem 1.2 says to let b and c be real numbers, let n be a positive integer, and let f and g be functions with the limits. The limit as x approaches c of f of x equals L, and the limit as x approaches c of g of x equals K. Then we have 5 different properties that fall under Theorem 1.2. So the first property that we want to look at is the scalar multiple property. This property said that the limit as x approaches c of b times f of x is equal to b times L. So our scalar here is b. notice that we can take our scalar out from the front of the function and put it in front of the limit and evaluate it that way. In other words, the limit of a scalar multiple is equal to the scalar multiple of the limit. The second property that we want to look at is the sum or difference property. This property says that the limit as x approaches c of f of x plus g of x is equal to the limit as x approaches c of f of x plus or minus the limit as x approaches c of g of x. In other words, the limit of the sum or difference is equal to the sum or difference of the limits. The third property is the product property. This property says that the limit as x approaches c of f of x times g of x is equal to the limit as x approaches c of f of x times the limit as x approaches c of g of x. In other words, the limit of the products is equal to the product of the limits. The next property that we want to look at is the quotient property. This property says that the limit as x approaches c of f of x divided by g of x is equal to the limit as x approaches c of f of x divided by the limit as x approaches c of g of x, provided that the limit as x approaches c of g of x is not equal to 0. In other words, the limit of a quotient is equal to the quotient of the limits. The last property that we want to look at is the power property. This property says that the limit as x approaches c of f of x raised to the n is equal to the limit as x approaches c of f of x raised to the n. Now let's practice using those properties. In example 2, we're asked to find the limit as x approaches 2 of 4x squared plus 3. So the limit as x approaches 2 of 4x squared plus 3 can be separated using the sum property into the limit as x approaches 2 of 4x squared plus the limit as x approaches 2 of 3. And then we can use the scalar multiple property to bring the 4 out in the front. So we have 4 times the limit as x approaches 2 of x squared plus the limit as x approaches 2 of 3. And then we can use property 5 so that we have 4 times the limit as x approaches 2 of x squared plus the limit as x approaches 2 of 3. And so for both of the limits that we have, we can use direct substitution. For the first one, we have 4 times the limit as x approaches 2 of x, which is the identity function. We know that that's going to be equal to 2, so we can substitute 2 in there. And then for the second one, we have the limit as x approaches 2 of 3, which is a constant function. So we know that that's just going to be equal to the constant 3. And so we're going to get 4 times 4, which is 16, plus 3, which equals 19. And so the limit is reinforced by the graph shown in the figure. Notice that f of 2 is equal to 19, and that's just because this is a continuous function, so the limit value should be the same as the function value. Now here's one for you to try. We're looking for the limit as x approaches negative 2 of 2x cubed minus 3x squared plus x minus 2. Now I would like you to pause your video and try to work out this problem, and then unpause it to see if your solution matches my solution. So you should have gotten negative 32 as your limit. Notice that the limit is separated into 4 different limits using the sum and difference property. Then the scalar of 2 is brought out to the front of its limit. The scalar 3 is brought out to the front of its limit. And then we use the power property on the first 2 limits. After that, we use theorem 1.1, which is the property of direct substitution, to finalize our solution. That brings us to the next property that deals with limits of polynomials. The function that we looked at in example 2, p of x equals 4x squared plus 3 is a polynomial. Now we know that polynomials are continuous. Therefore, we should be able to use direct substitution. So instead of using all those properties that we used in example 2, we could have just directly substituted into it to find the limit. So the limit as x approaches 2 of p of x is equal to p of 2, which equals 4 times 2 squared plus 3, which equals 19. The limit that you just found for the you try it problem that you just did was also of a polynomial function. Therefore, you could have used direct substitution for that one as well. And the last point that I want to bring up from this slide is that not only is the direct substitution property valid for all polynomial functions, but it's also valid for all rational functions with non-zero denominators. And that's because those will also be continuous. And that brings us to theorem 1.3, limits of polynomial and rational functions. If p is a polynomial function and c is a real number, then the limit as x approaches c of p of x is equal to p of c. If r is a rational function given by r of x equals p of x divided by q of x, and c is a real number such that q of c is not equal to 0, then the limit as x approaches c of r of x equals r of c equals p of c divided by q of c. So we need to pay attention to this requirement that q of c cannot be equal to 0. In other words, c must be in the domain of our rational function in order for us to use direct substitution. So let's see if we can apply theorem 1.3. In example 3, we're asked to find the limit as x approaches 1 of x squared plus x plus 2 divided by x plus 1. Now, what we want to keep in mind again is that c, which in this case is 1, must be in the domain of the rational function in order for us to directly substitute. So what we want to do is look at the denominator. The denominator is x plus 1. And if you put a 1 in there, then that's going to cause the denominator to be 2, which means it's in the domain. The only thing that would throw it out of the domain is if it caused your denominator to equal 0. Therefore, we can go ahead and directly substitute. So then the limit as x approaches 1 of x squared plus x plus 2 divided by x plus 1. So we have 1 squared plus 1 plus 2 over 1 plus 1, which equals 4 over 2, which equals 2. So the limit as x approaches 1 of x squared plus 2 over x plus 1 is equal to 2. Notice that the answer that we got is validated if you look at the graph on the right. You can see the limit as x approaches 1 is equal to 2. Now it's time for you to practice theorem 1.3. You're going to be looking for the limit as x approaches 2 of 3x plus 5 over x plus 2. So please pause the video and work this limit and then unpause it and see if you have a solution that matches mine. So you should have noticed that 2 is in the domain of the function. Therefore, you can use direct substitution, and you should have got 11 over 4 as your answer. Now that we've looked at polynomial functions and rational functions, which are just 2 of the 3 basic types of algebraic functions, we're going to look at the third type of algebraic function, which involves a radical. So theorem 1.4 says to let n be a positive integer. The limit below is valid for all c when n is odd, and is valid for c is greater than 0 when n is even. The limit as x approaches c of the nth root of x is equal to the nth root of c. Let's practice using theorem 1.4. In example 4, we're asked to find the limit as x approaches 8 of the square root of 3x plus 1. So that's just going to equal the square root of 3 times 8 plus 1, which is the square root of 25, which equals 5. Now it's time for you to practice using Theorem 1.4. Please pause the video and find the limit, and then when you're done, you can check the solution and see if it matches mine. So you should have just used direct substitution and plugged 6 in, so we get 2 times 6, which is 12, plus 4 is 16. You take the 4th root of 16, which equals 2. Now let's look at limits of trigonometric functions. You've seen that the limits of many algebraic functions can be evaluated by direct substitution. The 6 basic trigonometric functions also exhibit this desirable quality, as shown in the theorem below. For Theorem 1.6, we're told to let C be a real number in the domain of the given trigonometric function. Then 1, the limit as x approaches c of sine x equals sine c. 2, the limit as x approaches c of cosine x equals cosine c. 3, the limit as x approaches c of tangent x equals tangent c. 4, the limit as x approaches c of cotangent x equals cotangent c. 5, the limit as x approaches c of secant x equals secant c. And 6, the limit as x approaches c of cosecant x equals cosecant c. Now let's practice using Theorem 1.6. For example 5, we're asked to find the following limits. The first limit is the limit as x approaches 0 of tangent x. We're going to use direct substitution here, so that's going to be equal to tangent of 0. Now I put a unit circle here because I thought it might be helpful. Remember that tangent is sine over cosine. And if you remember from the unit circle, cosine is your x values and sine is your y values. So at 0 degrees, these are your coordinates. So sine over cosine is going to be 0 over 1, which equals 0. So our limit here is 0. Now let's look at part B. Here we're asked to find the limit as x approaches pi of x times cosine x. The first thing that we'll do is use the product property. So that's going to equal the limit as x approaches pi of x times the limit as x approaches pi of cosine x. And now we can use direct substitution. So that's going to equal pi times cosine pi. So we can look over at our unit circle. Notice at pi radians that the cosine value, which is the x value, is -1. So our answer is going to be pi times -1, which is just negative pi. For part C, we're asked to find the limit as x approaches 0 of sine squared x. We can use direct substitution here as well, but first we need to rewrite it. This is going to equal the limit as x approaches 0 of sine x squared. So sine squared x is the same thing as sine x squared. And then we use direct substitution, so we get sine of 0 squared. If you look over at the unit circle at 0 radians, the sine value, which is the y value, equals 0. So we get 0 squared, which equals 0. Now it's time for you to practice using Theorem 1.6. Please pause the video and find these limits, and then unpause it and see if your solutions match my solutions. Okay, so for part A, the limit as x approaches 5 pi over 3 of cosine x, we just directly substitute 5 pi over 3, and so we end up with cosine of 5 pi over 3. Notice that 5 pi over 3 is over here in the fourth quadrant. So cosine is the x value, which is 1/2, so the limit equals 1/2. For part B, we're asked to find the limit as x approaches 7 of secant of pi x over 6. So we can use direct substitution again. And also I just switched out pi and x so that I got secant of 7 pi over 6. And then we use the trig identity that secant x equals 1 over cosine x. So this equals 1 over cosine of 7 pi over 6. And then cosine of 7 pi over 6, well, 7 pi over 6 is over in the third quadrant. And the cosine value is the x value, negative root 3 over 2. So we have 1 over negative root 3 over 2. And then we can just flip it. So we have negative 2 over root 3. And then by rationalizing the denominator, by multiplying root 3 on the top and the bottom, we get negative 2 root 3 over 3. The next property of limits that we want to look at is the limit of a composite function. Theorem 1.5 says, if f and g are functions such that the limit as x approaches c of g of x equals L, and the limit as x approaches L of f of x equals f of L, then the limit as x approaches c of f of g of x is equal to f of the limit as x approaches c of g of x, which is equal to f of L. Now let's practice using theorem 1.5. For example 6, we're told to find two different limits. The first limit is the limit as x approaches 0 of the square root of x squared plus 4. So in this problem, the square root of x squared plus 4 is f of g of x. So we're going to write that down first. That means the inner function, g of x, equals x squared plus 4. And the outer function, f of x, is just the square root of x. And so we're going to find first the limit as x approaches 0 of g of x. We have the limit as x approaches 0 of x squared plus 4. That's equal to, by direct substitution, we have 0 squared plus 4, which equals 4. And then we're going to find the limit as x approaches 4 of the square root of x, of f of x. By direct substitution, that equals the square root of 4, which equals 2. So now we can apply theorem 1.5, and we can say that because the limit as x approaches 0 of x squared plus 4 equals 4, and the limit as x approaches 4 of the square root of x equals 2, then the limit as x approaches 0 of the square root of x squared plus 4 is equal to the square root of 4, which equals 2. Now let's look at part B. For part B, we're asked to find the limit as x approaches 3 of the cube root of 2x squared minus 10. So in this problem, f of g of x is equal to the cube root of 2x squared minus 10. So the inner function, g of x, equals 2x squared minus 10. And the outer function, f of x, is the cube root of x. So first we're going to take the limit of g of x as x approaches 3. So we have the limit as x approaches 3 of 2x squared minus 10. By direct substitution, that equals 2 times 3 squared minus 10, which equals 8. And then we're going to take the limit of f of x as x approaches 8. So we have the limit as x approaches 8 of the cube root of x. That equals, by direct substitution, the cube root of 8, which equals 2. Theorem 1.5, and we can say that because the limit as x approaches 3 of 2x squared minus 10 equals 8, and the limit as x approaches 8 of the cube root of x equals 2, then we conclude that the limit as x approaches 3 of the cube root of 2x squared minus 10 is equal to the cube root of 8, which equals 2. Now it's your turn to practice using Theorem 1.5. I'd like you to please pause the video and work these two problems and see if you can come up with the limits, and then unpause your video and see if your solution matches mine. So for part A, we're asked to find the limit as x approaches 2 of the cube root of 12x plus 3. The composite function f of g of x is equal to the cube root of 12x plus 3. The outer function f of x equals the cube root of x, and the inner function g of x is equal to 12x plus 3. We first take the limit as x approaches 2 of g of x, which is 12x plus 3, and by direct substitution, we see that that equals 27. Then we take the limit as x approaches 27 of f of x, which is the cube root of x, and by direct substitution, that equals 3. So then we can apply Theorem 1.5, and we can say that because the limit as x approaches 2 of 12x plus 3 equals 27, and the limit as x approaches 27 of the cube root of x is equal to 3, you can conclude that the limit as x approaches 2 of the cube root of 12x plus 3 is equal to the cube root of 27 is equal to 3. For part B, we're asked to find the limit as x approaches pi over 3 of cosine cubed x. The composite function f of g of x equals cosine cubed x. We need to note that cosine cubed x can be written as cosine x cubed. And it's easier to see when it's written that way that the outer function f of x is x cubed, and the inner function g of x is cosine x. So first we take the limit as x approaches pi over 3 of g of x, which is cosine x. By direct substitution, we get cosine of pi over 3. If you look up here at the unit circle in quadrant 1, we have pi over 3, and the cosine value is the x value, which is 1/2. So that limit is equal to 1/2. And then we take the limit as x approaches 1/2 of f of x, which is x cubed, and that equals, by direct substitution, 1/8. Then we can go ahead and apply Theorem 1.5, and we can say that because the limit as x approaches pi over 3 of cosine x is equal to 1/2, and the limit as x approaches 1/2 of x cubed is equal to 1/8, you can conclude that the limit as x approaches pi over 3 of cosine cubed x is equal to 1/2 cubed, which equals 1/8. So that brings us to the end of part 1 of this section. Next, you'll want to watch part 2, which is a strategy for finding limits.